Hello, my name is Jessica Srail, and today I will be presenting the VLE equations you'll use in your 2200 class. This is a part of the Student Active Learning Initiative put on by the CBE department. A quick introduction to myself: I am a senior currently, graduating spring 2021. I am involved with AICE and the IBE program through board positions and mentorship programs, so I really love seeing others understand foreign concepts for the first time. Hopefully, these concept introduction videos are a way to help introduce and motivate you to learn the material in the course. So we'll start off with a brief introduction to VLE. VLE stands for Vapor-Liquid Equilibrium. A quick example of this that you can likely visualize is lakeside air humidity. You have a constant equilibrium between the water in the lake and the water in the air. When at this equilibrium, you have equal rates of water molecules going into the water from the air and water molecules evaporating into the air. So when we talk about vapor-liquid equilibrium, what do we generally want to know? We want to figure out the partial pressures of the vapor phase and the mole fractions of the liquid phase. These both essentially describe what percent of each component is in each phase, and in problems you may see both of these variables referenced in the all-encompassing term composition. The sum of all mole fractions will be equal to 1, and the sum of all partial pressure components will equal the total pressure. For example, when considering lakeside air humidity, the sum of all partial pressures would equal the pressure of the atmosphere, which is around 1 atm. In addition to these, with vapor-liquid equilibrium, we are also looking for bubble and dew points of a given mixture. In a pure substance, these are the same temperature, the boiling point. However, when we have a mixture, these are distinct regions. The bubble point is the temperature at which we see the first bubble appear in a liquid, and the dew point is the temperature at which the first drop of dew condenses from the vapor phase. In between these 2 points is where we see vapor-liquid equilibrium in a mixture. If these terms aren't making sense right now, no worries. You'll go over them and work with them extensively in class. Additionally, the video on VLE diagrams gives a graphical representation of these points, which I found really helpful while learning VLE since I'm a visual learner. Even though VLE diagrams really helped me understand VLE as a whole, they're not the end-all be-all, at least in 2200. You might also be wondering why we're even introducing these equations, and the answer is that when you're physically working with VLE diagrams and doing calculations by hand, there can be a lot of error inherent in just working with small graphs and being a human being. As such, working with pen and paper VLE diagrams is not the most precise, but is great for back-of-the-envelope calculations. However, I do want to mention that the graphs themselves are very precise, as they're created from actual data on a mixture. So if you're working in a program like ChemCAD, those diagrams are really powerful, precise, and accurate tools, and can expand further than the following equations in areas such as non-ideal mixtures. The following equations are good for classroom calculations, as well as ideal VLE that might not have a specific TXY or PXY diagram for the temperature or pressure you're looking for. Let's finally get into the actual laws now. Before the explanation, I want to stress that both laws are based on the assumption that we're working with an ideal solution. If you encounter a problem where the mixture is non-ideal, looking into TXY and PXY diagrams will be your friend. Anyways, first we have Henry's law, which states that the partial pressure of component A equals the vapor mole fraction of component A times the total pressure, which in turn equals the liquid mole fraction of A times the Henry's law constant of component A at a specific temperature, denoted T. I've also included brackets here that give which units each variable here will be in. Moving on to the other VLE law we see that Raoult's law is very similar to Henry's law. Most of the variables are the same as in Henry's law, except instead of Henry's constant here, we use the vapor pressure of pure component A at temperature T. I do want to stress that even though the equations look almost the exact same, the Henry's law constant is not the same as P star. This will hopefully become clearer in the next slide. The major distinction between these two equations is what I'll refer to as the constant. Realistically, the values we'll use for the Henry's law constant and vapor pressures vary with temperature, but since it's a variable that doesn't really change in our equation while we're working with it, I'm going to call it a constant. This constant actually has a lot to do with what the equation can solve for. As shown here, Henry's law is really only valid at a liquid mole fraction of A close to 0, while Raoult's law is valid when the liquid mole fraction of A is close to 1. This is exemplified by the graph to the right. Henry's law is really quite accurate at low mole fractions in the liquid phase, but as you go up in liquid mole fraction of the component, it deviates quite significantly. I remember it was pretty hard for me to recall which law to use in which situation, and the way I ended up thinking about it was this. I know Raoult's law works with vapor pressure since Henry's works with Henry's constant. So if you're performing a calculation using the vapor pressure of substance A, your liquid phase should probably have a pretty high mole fraction of A for that calculation to be accurate. I'd also like to reiterate something I mentioned previously, which is that both of these equations only work with ideal mixtures. It might be confusing to call something a law and then not have it be able to apply to any situation, but the definition of scientific laws is that they are statements based on repeated experiments or observations that describe or predict a range of natural phenomena. So calling these laws is not incorrect, and they will provide accurate results, at least when we're working within their range of validity. In this class, that will mean using Henry's law for dilute mixtures, and while Raoult's is more accurate when the liquid mole fraction of our component is close to 1, Raoult's will likely be used for calculations on any ideal mixtures that are outside the realm of Henry's law. Going more into the actual quote-unquote constants, we know that the Henry's law constant will be given to us in some form or another if we are going to use it. It could be in a table or just written out in the problem. However, Raoult's law uses the vapor pressure of the pure component that we're interested in at the temperature we're looking at. This value is sometimes given in the problem, but not always. Especially in homework problems, you're more likely to be tasked with finding the vapor pressure on your own. There are 4 ways to do this. Tables are the easiest and most accurate, but they aren't always available. Cox charts are also relatively quick compared to other methods, but they're not as accurate as others, so they may not be taught in your class as they're already being phased out of textbooks. Both the Antoine equation and the Clausius-Clapeyron equation are empirical and give pretty accurate values. You'll almost certainly go over these methods more in class and learn how to calculate them, but if you want to look into them in advance, the Antoine equation and the constants you can use are in table B4 of the 4th edition of Felder and Rousseau, and the Clausius-Clapeyron equation uses a substance-specific constant that you can find if you already know the latent heat of vaporization and the vapor pressure of a substance at a specific temperature. But don't feel too overwhelmed by this. You'll do examples and work a lot more with these equations in class. All right, now for the fun part. I'm going to go into solving the first part of an example you might see in class. This might look something like the block of text on this slide. An unopened can of soda has some room at the top to allow for carbon dioxide. This carbon dioxide is in VLE with the liquid below, which causes the bubbles and fizz we're used to seeing. If a can is bottled at 2.5 atm and 2 degrees Celsius, and the Henry's constant for carbon dioxide in soda is 30 atm at 25 degrees Celsius, what is the mole fraction of carbon dioxide in the liquid phase at 25 degrees Celsius? Is our answer reliable? And at first, this potentially seems a bit overwhelming. So what I like to do is highlight or underline the most important parts of the problem. Bottled at 2.5 atm is important to me because that's going to give the partial pressure that the carbon dioxide is at. The Henry's law constant is 30 atm at 25 degrees C, which basically indicates that we'll be using Henry's law. But we could also figure out, just by doing some cursory thinking, is carbon dioxide highly soluble in water? And the answer is not really. And we can justify that by just thinking about the fact that carbon dioxide doesn't easily diffuse into our coffee, tea, or water when we blow on it. So soda is probably similar and wouldn't have a high liquid mole fraction of carbon dioxide. So Henry's law would be valid. You may also wonder why I'm not including 2 degrees Celsius in the highlighted portion. And that is because that is just the temperature that the can was bottled at. And now we're looking at a new, different equilibrium at 25 degrees Celsius. If we were trying to find the mole fraction of carbon dioxide in the liquid phase at 2 degrees Celsius, then we would need a different Henry's law constant at that temperature. With that information, we now know that the partial pressure of CO2 is 2.5 atm, which is equal to the liquid mole fraction of CO2 times the Henry's constant, which we deduced is 30 atm at 25 degrees Celsius. That's all information we were able to get from the problem statement. Now we just rearrange the equation in that first line to solve for xCO2, and we end up with a liquid mole fraction of 0.0833. That's dimensionless because it's a mole fraction. So now we ask, is our answer reliable? That was the last part of the problem, and the answer is yes, it is. Henry's law is applicable at low values of liquid mole fraction, and since our mole fraction was calculated to be 0.0833, we can say that's pretty close to zero, and that Henry's law is trustworthy here. If we wanted to take this a step further, we could do something like figuring out how many actual grams of carbon dioxide are dissolved in the liquid of the unopened can, or how the pressure and mole fractions change once the can is opened. But this is just a quick introduction. So at this point, you may be wondering, why should I care? I always found it important to care because Dr. Clay would ask me the 4 methods of finding vapor pressure every chance he got, so I assume he will do the same to any chemical engineering student that crosses his path. Additionally, it will actually be used across a lot of your current and future coursework. It'll definitely be used through the throughout the entirety of the multi-phase systems chapter, and will realistically come into play almost any time you have phase changes, since phase changes in chemical engineering are usually between the gas and liquid phases. You'll definitely look into the energy side of VLE as you move into energy balances also. In relation to other chemi courses, vapor-liquid equilibrium is essential to a lot of separation processes, and as a result, you'll certainly see it in that class and in unit ops, where you'll actually be working with those separation processes. You'll also see it a bit in thermodynamics, where you'll actually expand the definition of vapor-liquid equilibrium to this big equation, which is really just a more complicated view of vapor-liquid equilibrium. When you simplify this equation with the assumptions we used previously, it just turns into Raoult's law. In industry, vapor-liquid equilibrium is essentially the basis for distillation. And if we look at this little pie chart to the left, we can see that distillation accounts for a huge amount of energy consumption in the US. And if you wanted to know the actual math on all those percentage points, distillation accounts for approximately 8% of all energy usage in the US. Honestly, the fact that a single process takes up more than 1% of all energy the US consumes shows how widely used and important distillation is to so many processes. Some big fields that are known for using distillation include the oil industry, which uses distillation for many different processes, such as separating different octanes of fuel, the liquor industry for concentrating ethanol and spirits, and the food industry, which uses distillation for flavor extracts. I hope you found this presentation at least a little bit useful for you and a good introduction to some vapor-liquid equilibrium concepts and equations. Good luck in your coursework, and thank you for watching.